Hello, everyone. Welcome back to Advent of Code. As promised, I finished up episode 6 off camera, and I'm going to give you episode 6, day 6. It was my 6th episode, but it's now the 7th. I didn't finish it off during any episode, right? It was between. But it was the 6th day of Advent of Code. So I'm going to give you guys a tour of what I did after attempting the ST array stuff. So basically what I did is I decided that the ST array stuff is just way too complicated. Well, no, that's not true. Rather, yesterday's exercise was useful because I learned some things, right? I got practice using ST and arrays. I looked up how to do those things. And I built a simple array, evaluated it in ST, and got the result. I also thought of an algorithm that would perform asymptotically better than the naive and n squared thing. I think it would perform asymptotically better, but I'm not sure. But it was going to be a lot of work to actually implement that. And remember, before we even started, I said it's 8 million operations? A computer can handle that. So I sat down and tried to do something faster, and I thought it was something faster, but implementing it was going to be a lot of work. So I decided to just throw that out and do the sort of obvious thing of just iterate over every point on the grid and find what all of the destinations that are closest to it are. Throw out the ones that are in infinities, and otherwise choose the one with the largest area. And so I end up needing a lot of stuff from data list, more than I typically do. So what did I end up doing? I defined type. I already had this, right? Coord is a pair of ints. This destination is actually kind of interesting. I forget if I had defined this in the first version or not. Actually, I guess I can see, right? Well, I kind of moved things around, right? I had not defined it yet. Okay. So at first, destination seemed like the kind of thing that should be a data declaration, right? An actual, I made this a destination that contained 2 fields of type ID and coordinate. But I was implementing some stuff later that made me realize that that was sort of too rigid a type. This existing destination type is equivalent to the tuple type, right? It's suppose that we had done. Really? Suppose that we had done instead data destination equal destination ID coord. These are very, very similar types, right? They're not actually isomorphic because there are more undefined values of this type than of this one, but if you ignore that, they're basically the same. But there's another difference, which is that the tuple type is parameterized, right? This is sort of the same as it's shorthand for this type, right? The tuple, the type of a pair applied to both the types ID and coordinate, whereas mine is not. I could have done that by saying destination AB equals destination of AB, and then use ID and coordinate when I want. But I thought, when am I ever going to want to change the value that's in a destination, right? Or the type of value in a destination? When would I ever want to store something else? And it turns out there was actually a good reason to do that, which is that tuple participates in a bunch of type classes. It's a functor, it's applicative, whatever. And it turns out that f-mapping into a destination is really useful because you keep the ID around, but you can perform operations on the coordinate. And I ended up doing that when I calculated the closest points to another point. So this turned out to be a better type simply because I can change the type parameters and use fmap. I define a distance to be like, it's an int, but wrapped up in dist. And to get the int out of that, you call getDist. This was so I don't confuse... Like, I defined two type aliases for int, ID and distance. This is so I don't accidentally mix those up. And I actually... This function took me the most time. Sort of, maybe. Of course, it's a very short function to write, and I wrote it very quickly. But I wrote it wrong. I wrote this. And hopefully you can see why this is wrong, right? I compared the x distance and added it to the y distance. And then I took the absolute value of that. And so I ended up like... There were some destinations that had 0 points that were closest to them. None at all. And I couldn't figure out what on earth could be causing that. Like, the point that the destination is at should be the closest to that destination, right? Well, it turned out that, like, there were other points that were, like... Because of this error, there were other points that were, like, basically... They shared exactly the same boundary, according to this incorrect absolute value calculation, as the real point did. And so it was always tied, never winning. Kind of interesting. But okay, this correct implementation is pretty simple. Bounds, I think we wrote on camera last time, but I moved it into its own function. Points within was sort of useful to produce a list of points so that you can iterate over them. Since we weren't actually iterating over all the points before, so that wasn't necessary, but now it is. We just want to produce... We want to compute a property of each point, and so to do that, we produce a list of all the points. Fine. And then here's part one. Actually, do I do anything interesting before I pass to part one? No. Actually, that's not quite true. I added this step here in between parsing and calling part one, which is to label each of the points with an identity. An identifier, perhaps. This is so... I just need something that a point has. I guess I don't even need that. I could have used the point's actual coordinates, but it's kind of nice to have IDs, I think. It made it a bit easier to debug when I was looking through why my distances were wrong. And that, like, I could see, okay, yeah, here's point 17. I remember. Point 17 is the problem. Yeah, 17 and 33 were in the same location, effectively, according to this bad distance calculation I had originally written. So part one is, like, a pretty big function. I mean, I know... How do I forget how to count lines in a region. Count lines... Count words region. So it's only 12 lines long, including the type signature at the top. But... And in many languages, this would be like a laughably small function. But in Haskell, this is gigantic, I think. I really try not to write functions even this large because there's so much going on in each of these tokens. They all do so much. And so the more you can split it up, the better. That's why I split up bounds and points within and so on. And I'm not really sure of the structure of this, like whether this was the best way to do it. Really, I could have made everything in aware clause and just, like, had this be the body. And then have, like, move these two declarations into the where clause as well. But it kind of feels to me like... I don't know. I don't have a good reason. For what goes down here and why this stuff doesn't. I guess this feels like defining properties of the input, right? Like this is not exactly doing the computation. It's defining how the computation could be done if you had an input, kinda. But like not really, because bounds, like I don't know. This I don't know. It's stuff that you need in order to compute the stuff in part 1, but it doesn't feel like totally central to it. Except for consider, which obviously like is, we'll get to it, but it's like the most, it's kind of the core of the whole algorithm in a way. But it kind of like making it in a where clause kind of feels good because we're like calling fold map on it, and I don't know. I prefer to define functions in a where clause than in a let, for no good reason. Like either one is fine, but anyway, so sort of the same thing, whether it's a where or a let really. But so we compute the bounds, and we save both the actual bounding box itself and we break it up into components and construct all the points. And we define a little helper function to tell us whether a coordinate is part of an infinite area. And that's just whether it's on the edge. We talked about that last time. Finally, the really interesting thing is in consider point and in how I use fold map consider over points. Consider is a function which takes in a point and produces as a result, you know, this. A pair of a list of IDs that point is part of. And you know, I wonder if no, fold map was the right thing. Yeah. So mempty is an empty list. Like I could have, well, no, it's not here. So do we have Intero mode? So what is the type of mempty, right? It's for any monoid, which is like monoids are types which have a combine operation that is associative as well as an identity element. For example, concatenating lists. There's an identity element, which is the empty list, and an associative operation, which is concatenation. And so mempty as a list of int is just an empty list. But pairs are also monoids if their elements are empty, are monoids. So we can say what is mempty as a list of int and a string, like a pair of those things. And it's the empty list and the empty string. So we are returning a pair of a list, which is a possibly empty list, of destinations whose area this falls into, right? There's either 1 or 0 of those. And also, the second half of the tuple that we return is a set of destinations that we have determined include an infinite area. So this, yeah, this is also either like singleton or empty. So basically, we compute, and it's nice just like how concise this is. Obviously, you could do this in one line in another language, right? As like a list comprehension in Python or something. But I just think it's so cool to be able to write map, fmap, distance point. Like we're partially applying so many functions here, right? Distance is a function of 2 arguments, but we only give it 1. And that's point. We're partially applying it. And fmap takes 2 arguments, a function and a functor. We give it only one and partially apply it. Map. Okay, finally something we call with all its arguments. We take that function we built up by composing fmap distance and point and call it on all the destinations. Here's where I'm fmapping into that tuple I talked about earlier. I started with a list of destinations, which is to say pairs of IDs and coordinates. But by fmapping into that list, I now have a list of pairs of IDs and distances. Pretty cool, huh? So anyway, I get the distances of all the points, and I compute the set of points which are tied for the closest. And this function was kind of I wrote this wrong once, because I didn't understand the contract of group by, but after that it wasn't too bad. I guess I actually also did it twice wrong because I put a first here instead of a second, but whatever. So the idea is we take the distances and we sort them comparing by second element, i.e. the distance. Having sorted them, we now group them into groups of adjacent elements which have an equal distance. That's what this group by equal on second does. And then we take head, the first group. So that is after sorting by distance and collating a list of all the things that are tied, we take the first closest item. That's the list of all ID distance pairs that are closest. And then we say, well, was that empty or not? Did it have a single element or some other number of elements? If it had just one element, an ID and a distance, then we actually found a point, and we emit ID and this set. Now, here's a trick. This set may be empty or not, right? This is a list comprehension that says return ID provided that the point is infinite. So it's like a comprehension that's either 0 or 1 elements. We only want to emit this list if we found a place that has an infinity. So we may return an empty list, or a pair containing an empty list and an empty set. Or we may return a pair containing a singleton list and a singleton set. Or we may return a pair containing a singleton list and an empty set. Okay. So why sets? Why pairs? That gets back to up here, fold map. So fold map is a cool function. What is the type of fold map? Fold map takes something foldable, for example, a list, and something monoidal, for example, a pair of list and set, and a function which converts elements from the list into values of that monoidal type. And it takes a list, and it produces a single element of that monoidal type. So we map over the list, producing a bunch of these monoids, and then we use the combination property of the monoid to concatenate them all together. So I don't have to do a bunch of unpacking of the lists that I returned at each step, adding to one, adding to the other, combining them together. I can just emit one monoidal thing for each point I look at and allow fold map to combine them for me using the monoid properties of lists and sets and pairs. So having done that, we fold map consider over the points and get back a pair of a list and a set. So the list is one entry with one identity for each destination that we started with. No. Let's try again. It's a list of identities, identifiers for destinations, and the number of times an identity is repeated is how many points on the grid had that destination as their single closest destination. That's what owners is. And infinities is just a set of all of the destinations that were found to contain infinite areas. So we filter from the owners those which are not in the set of infinities. And then we just, like, sort them so that all of the IDs for the same destination are adjacent. Group them together so that we have a list of lists, and compute the length of each list. That'll be how many times that identity appeared. Choose the largest such length, and that's the answer we were supposed to give. So, kind of a lot going on, right, for this tiny little function. If you're used to, say, Java or Python, like, you know, people say you shouldn't write functions longer than 30 lines or whatever in Java, but people often do. And, like, 12, you just, like, wouldn't even really notice most of the time. It's all just calls to 12 getters, right? So that was part one. And having debugged a couple of things here, the simple algorithm, of course, worked. Have I made any changes here? Yes. Why? What? Oh, sure. But okay. So what I want to show you now is... Why do I have all these diffs? I must have... I know I did a checkout. I did a checkout of the parent commit, but that should have left the index pointing to the same thing. I must have done something weird. Because, like, we're here. But our index is this? No. Our index is also this, but our working copy is this? No, our working... I don't know. It's weird. I don't know. I'll just reset to master and it'll be fine. So let me show you part two, and I guess we'll go look at... Part two was actually way easier, because you didn't have to think about, like, what it means to be part of an infinite area. And it's very clear that the only thing you could really do is iterate over all the destinations here. So basically we're told, okay, well, we found area that's the largest open area around a thing. Now we're trying to find, you know, maybe I'll just read you the dang problem, huh? Find a region near as many coordinates as possible. For each location, add up the distances to all of the coordinates. That's every single one in our file. If the total of those distances is less than n, which in this example is 32, then you should include that point. Otherwise, you shouldn't. So we just iterate over all the destinations, adding up the distance to them, and see... Well, we iterate over all the points, and then for each point, we iterate over all the destinations, computing the total distance, the distance to each, and adding them all up. And whether that total is smaller or larger than 10,000 is what we're asked to find. So find the size of the region containing all locations which have a total distance to all coordinates of less than 10,000. So this was actually pretty simple. In fact, you can see that I didn't do very much. I lifted out points within. Yeah, I guess I somehow was showing you guys part two instead of showing you part one, but so little had changed that you could barely tell. So basically, like, I just took points within that was used in part one and lifted it out to the top level. And then part two is just this. Much, much simpler than part one, right? We just do to iterate over all the points, and then compute a property of the destinations, which is to map over the location of the coordinate of the destination its distance to the point we're considering, converting that distance from a distance to an int, sum the results, and return it. Right? And that's it. And then we just, outside of that list comprehension, we filter for items less than 10,000 and compute the length. And that's how many fit. There is some danger that, like, remember this, we're supposed to pretend we're on an infinite plane. And there is some danger that, like, one of the points, because I'm only computing the bounding box, right? I'm only working within the bounding box for destinations. And one point that, if all the destinations were quite compact, there could be points outside of this bounding box that would satisfy this condition. So if that were the case, we would have to be more careful. But it's not, so I'm just leaving it as is. Okay, so I think that we are done with this puzzle, and I'm going to make this a separate video from day 7. So that means we're done with this episode. Thanks for watching, and I'll see you next time.